stop sum, and today we are going to discuss about the first step analysis and how to calculate the expected reaching times and also how to calculate the expected number of steps to get into a particular destination. Now in this section, if you can remember, in the first step analysis we discussed about using the first step analysis. In the previous sections we discussed how to find out the probability of reaching a particular state in a given stochastic process. So the same first step analysis, so the same procedure we can apply in order to find the expected reaching time for a given state. So let's in this case, now if you can remember, when we were calculating the probability using the first step analysis, so we had a particular goal. So if you can remember the gambler's ruin, so there we were interested about the event that where you get ruined, or in other words where you end up the process having zero amount of cash in your hand. So we have a particular goal, and then we were interested about calculating the probability of that particular event or particular goal. So what we did was, how did we apply the first step analysis? We were looking for the possible first steps that we can take, or the possible options that we can take by given that we are in a particular state. So what we did was, in the first step analysis we have to calculate the probability of reaching that eventual goal, given that we are in option, let's say option number 1, and then we have to multiply that with the probability of option number 1. So likewise we have to consider all the options and get the summation. And here now today we are going to discuss about the first step analysis for expected reaching time. So there we are calculating the expected reaching time. So our goal is to calculate this expected reaching time. So how to use the first step analysis? Same as we are calculating the probability, we have to look for the possible options, and then we have to take the expected time given that we are in a particular option, and then we have to multiply that by the probability of reaching that option. So if we just quickly go through with the total the law of total expectation. So we know, if you have a random variable x, if it is depending on y, we know expected value of x is equal to this formula. That is, first you have to take the expected value of x given y, then you have to take the expected value of this content based on random variable y. So this we know we can just express this as summation on y, expected value of x given y equal to particular value of y, and multiply this by the probability of y. So in this case, if we take when it comes to the first step analysis, and when we are using this first step analysis in order to calculate the reaching time, so we can take the possible options as y's. Let's say we have option 1, option 2, option 3 likewise, and we can take x as the reaching time. So in this case we are interested about the expected value of x, that is, we are interested about the expected reaching time. So that is equal to summation expected value of x given the option multiplied by the probability of that particular option. So let's apply this to one single example and see. So if you look at this one, this is the first example, that is mouse in a maze. So if you look at now this, there is a mouse, so this one is trapped in a maze. So you can see, if you look at this diagram, which I have denoted by room, that is the maze. So there are three paths. If you take exit 1, this path, that is you can get out from the maze. But if you look at if this mouse takes exit 2, the mouse will come back to the same room after 5 minutes. And if you take exit 3, the mouse will then come back to the same room after 7 minutes. So we want to calculate the time taken for this particular mouse to leave the maze, starting from this given room. So we can see if this mouse is in this given room, there are three options. The mouse can take exit 1 or exit 2 or exit 3. So the exit options or the paths that mouse is going to select, we can take them as the possible options. Let's take them as 1, 2 and 3. And here now the mouse is in this room. That is the current situation. So if you take, we are interested about finding the expected time to get out from this room or from this maze. So we'll take X as the time taken for mouse to leave the maze. So you can see clearly, depending on the path, this expected time is changing. For an example, if this mouse at once, if this mouse selects exit 1, he will take only 3 minutes to leave the maze. But if he takes exit 2 first and then exit 1, then when he takes exit 2, then he will take 5 minutes to come back to the same point, and then again another 3 minutes to get exit. So altogether he has to spend 8 minutes. So you can see, depending on the path, this expected reaching time is changing. So we want to calculate the expected value of X. So that since it's depending on this paths, the paths we have taken as the options, which is denoted by Y. So depending on Y, X is changing. So when you are taking the expected value of X, we have to take the conditional expectation. So in this case, expected value of X is equal to expected value of Y, expected value of X given Y, and then again you have to take the expected value of this whole term depending on variable Y. So this is the law of total expectation. And then we know we can just write this as expected value of X given Y into probability of Y, where Y goes from 1 to 3 since we have 3 options. Now let's take this when Y is equal to 1. So that is expected value of Y is equal, X given Y equal to 1. So you can see, if you take the first exit Y equal to 1, the probability of taking first exit is 1 over 3. So the probability is 1 over 3 plus expected value of X given Y equal to 2. You can see the probability of taking exit number 2 is again 1 over 3. Probability of taking exit number 3 is again 1 over 3. So we can substitute the probabilities, that is expected value of X given Y equal to 2 into 1 over 3 plus expected value of X given Y equal to 3 into probabilities 1 over 3. So if you take the expected value, that is if you take expected value of X given Y equal 1, that is the mouse is taking first exit. If the mouse is taking first exit, that is the mouse has to spend only 3 minutes to go out or leave the maze. That is the expected value of this scenario, that is equal to 3 minutes. But if you take expected value of X given Y equal to 2, that is mouse is taking this second path. Then what will happen? Mouse has to spend 5 minutes. Again he will come back to the same point. That is, he'll come back to the same room. So again we have to consider about the time, the expected time that he has to spend to leave from the room. That is again expected value of x. So if you just substitute that, you can see expected value of x given y equal to 1 is 3 minutes. Expected value of x given y equal to 2 is 5 plus expected value of x, because he is coming to the same point after 5 minutes. Likewise, if you take the third path, that is you have to spend 7 minutes, but you come back to the same point. So that is 7 plus expected value of x. So now we have the values to this expectation. So we can substitute to the formula, and then when we substitute the values, so the only unknown term is the expected value of x. So what will happen when you substitute and simplify? You will get expected value of x is equal to 15 minutes. So this is how we use the first step analysis to solve or to find out the expected reaching time. This can be also done using the first step analysis if we just use quick notations. Right now we are interested about at the initial stage, the mouse is in this room and we want to find the time that the mouse will take to leave this maze. So we are interested about the expected time to leave the maze given that mouse is in this room. So this is what we are interested about, expected value of time to leave maze given that start in room. So let's take this as MR. So we want to find MR. So if we just check the possible options in the first, if you look at the diagram again, right, if you look at the diagram again, you can see in the first path, the probability of taking the first path is 1 over 3. So now you can clearly see based on this diagram, the probability of taking any path is the same. Since you have 3 paths, the probabilities are 1 over 3. And if you look at the first path, you have to spend 3 minutes and the probability is 1 over 3. The second path, 5 minutes, probability is 1 over 3. Third path, 7 minutes, probability is 1 over 3. So what you can do is, when you use the quick notation using the first step analysis, for the first path, probability is 1 over 3, you have to spend 3 minutes. Plus, second path, probability is 1 over 3. And you have to spend 5 minutes, but you will come back to the same point. So again we are coming to the initial point. So we have to again we are interested about the time to leave the maze given that we are in the room. So that is MR. So here we have to take 5 plus MR. And in the third option, the probability is 1 over 3. And then you have to multiply, the time is 7, but we will come back to the same point. So plus MR. So what will happen now, if you look at this equation, so the only unknown term is MR. So that is what we are interested about. So if you just solve this, simplify this one, you will get MR, which is equal to 15 minutes. So whatever the method you use, you'll get the same answer as before. So I hope that is clear with you. So when you are given with a diagram using the first step analysis, if you want, you can write down all the formulas which is associated with the total law of expectation and find out the expected reaching time, or else you can go with the quick notation of the first step analysis and find out the expected reaching time. And the next thing that we are interested about is the counting the steps, the expected number of steps that you have to spend to reach a particular goal or to get out from a given maze. So we are interested about the expected time and also the expected number of steps. So when we want to calculate about the expected number of steps, to reach a particular goal, again we can apply the first step analysis. So let's look at this diagram. So you can see in this diagram you have two rooms, room number 1 and room number 2, and you have an exit point. Let's look at the probabilities. You can see if you take room number 1, if you use this path, you can quickly get into the exit point and the probability is 1/3. And if you take room number 1 and this path, you will come back to the same room with probability 1/3. Or if you take this path, you will end up in room number 2. Again, the probability is 1/3. And if you look at room number 2, again you have 3 paths. If you use this path, it's the probability is 1/3. You will end up in room number 1. And if you use this path, again the probability is 1/3. You can exit. And if you use this path, again the probability is 1/3 and you will come back to room number 2. So our question is, starting from room num, what is the expected number of steps the mouse takes before it reaches the exit? Now the mouse is in room number 1. So the mouse wants to get out from this maze. So what is the expected number of steps that the mouse has to take in order to reach the exit point? So in this case, let's take M1 as the expected number of steps to get into the exit point or to finish, given that mouse is in room number 1. And let's take M2 as the expected number of steps to finish, given that the mouse is in room number 2. Okay, so let's use the first step analysis. Now if you take room number 1, right, we are interested about the expected number of steps to finish, given that the mouse is in room number 1, that is M1. So if we write a formula for M1, let's check the possible paths. Now if you straight away use this path, you can go to exit point. You have to only take only one step if you use this path. And the probability is 1/3. So that is 1/3 into 1 plus, let's say the mouse is going to use the second option. So the probability is 1/3 and then, but it will come back to the same point. So we used one step and come back to room number 1, and then again we are in room number 1. That is, again we are in the initial stage. That is, again we have to think about the expected number of steps that we have to spend in order to get out, where given that the mouse is in room number 1, that is M1. So that is why here we have 1 plus M1. Likewise, if you consider this path, again probability is 1/3 and here you have to spend one step, then you will come to room number 2. So that is, now we are in room number 2. So we are interested about the expected number of steps to finish, given that you are in room number 2, M2. That is why you have 1 plus M2. And likewise, if you look at M2, that is, now we are in M2. So if you use this path, probability is 1/3 and you have to use only one step, you can exit. Plus, if you use this path, probability is 1/3, you will come to room number 1, that is 1 plus M1. Plus, if you use this path, probability is 1/3, you will come back to room number 2 again, and so that is why 1 plus M2. So we have two unknowns, M1 and M2, and two equations. So we can solve this equation simultaneously and find out M1 and M2. So you will see M1 and M2 both are equal. It's equal to 3. So in this case, actually now when we want to use this when we want to find out the expected number of steps using the first step analysis. Now what we did here was, when we are applying this first step analysis to every possible option, we add a penalty when we are taking a step. For an example, when we write this equation for M1, now when you use this path, probability is 1 over 3 and we thought we are taking one step. So we add a penalty as 1. And then when you take in this path, 1 over 3 probability, penalty is 1, coming back to room number 1. So 1 plus M1. So likewise, for each and every possible option, we have added a penalty. So the same answer we can reach without adding this penalty, right? If we add this penalty only in the beginning, only once in the beginning. So that is when you are writing M1, we have to add a penalty, plus then we are considering about the possible options. So that is, if you are in the room number 1, first we write the penalty as 1 plus the first option is 1 over 3, then you can exit. You have nothing to worry, so we take it as 0. And if you take this path, the probability is 1 over 3, coming back to room 1. Then again we are interested about M1, so 1 over 3 into M1. And if you use this path, probability is 1 over 3, coming back to room number 2. So 1 over 3 into M2. Right? So in each case, we will have the same answer. You can just check whether you get the same answer. You can just write down the formula or the expression for M2 and solve it and see. Now in the method 1 we solved now. You can just check. You can write for M2 also and check whether you get the same answer. And here one last thing. Now if you can remember, in the previous sections we discussed when you have a random variable and when you are interested about its expectation, that expectation is equal to its probability. So if you can remember, if you take IA as a random variable, if IA is equal to 1, if A occurs, and 0 if it does not occur. So we have the proof, and we have already proven when you take the expected value of this indicator random variable, that is equal to probability where IA is equal to 1, or in other words, that is equal to the probability of event A. So if we just consider about the conditional expectation, right? If this indicator random variable has a condition, so that is probability of A, that is equal to expected value of IA. So in other words, that we can find this is equal to, if there is a conditional variable as Y, that we can find this expectation by expected value of IA given Y, and then we have to take the expectation of this term with regard to random variable Y. So that is, in other words, if you take the probability where this IA equal to R given Y, and then you have to multiply this by R. You have to take the summation where R is equal to, R goes from 0 to 1. So since this is an indicator variable, R can take only two options, either it's 0 or 1. So if you substitute 0 here, that is 0 into probability IA is equal to 0 given Y, plus 1 into probability IA is equal to 1 given Y. So the first term will cancel out. Then we will have probability IA is equal to 1 given Y. That is, IA is equal to 1 means the event is happening. That is event A. So in other words, we can write probability A given Y. So we can nicely see when you take the probability of A, right? Probability of A is equal to expected value of IA given Y, and then the whole thing expectation of Y, and this is equal to expected value. For IA, you can replace by event A, that is probability A given Y, the expectation with regard to random variable Y, it's equal to probability A. Right? So that is any random variable, whether it's discrete or continuous, and for any set of values, whether it's a discrete set or a continuous set, right? If it is a discrete random variable and for any set of values S, you can write this equation, the probability of a given event, a probability of this random variable X for any set of values S, that is you can write as this conditional probability, and that is for the discrete case, and the same thing you can just use for the continuous case. So we'll see how to use these expectations with an example. So here it is the example of probability as a conditional expectation. Now it's about the lottery, buying a lottery. Now let's say there are 1 million people and 1 million people have bought tickets, and each person has a 1 million of chance of selecting the winning numbers. So if more than one person selects the winning numbers, what will happen? They will choose the winner at random from all the winners. So now let's say you have also bought a ticket and now you are 1 in a million players. So what will happen? We are interested about calculating the probability of winning, probability of you become the winner. If you have the winning numbers, if your ticket matches with the winning numbers, we are interested in calculating the probability of winning, saying that you have the matching all the matching numbers in your ticket. So let's say if you take Y is the number of other matching tickets out of other 1 million tickets sold. So you have one ticket with matching numbers. If you take the other number of tickets with matching numbers as Y, if there are no other tickets with matching numbers, that is definitely you are the winner. So you are lucky and you will be the winner if Y is equal to 0. You will definitely win. And so you can see, if you take any ticket, there are only two possibilities. Either you win or either you lose. So it's a binomial process. But in this case, if you take the number of tickets, that is 1 million. And the probability is 1 over 1 million. So if you take NP, it is close to 1. So we can use the Poisson approximation here. So that's why if you take the other winning tickets as Y, it's having a Poisson distribution with lambda approximately equal to 1, because NP is approximately equal to 1 here. So in this case, if you take what is the probability, if you take the probability function of Y, if Y is having a Poisson distribution, the probability function of Y, that is e to power minus lambda, that is minus 1, lambda to power Y, that is 1 to power Y, divided by factorial Y. So when you simplify, that is 1 over e into factorial Y. So this is the probability function of Y. So here you can find the probability where Y equal to 0, Y equal to 1, likewise. So if Y gets equal to 0, you are very lucky, you will get the prize, because the number of tickets with matching numbers will be equal to 0. So that is the probability that yours is the only matching ticket, that is the probability having the only matching ticket with you. So for that case, Y should be equal to 0. So here if you substitute y as 0, that is 1 over e into factorial 0, that is 1 over e, that is 0.368. So this is the probability that you will win if you have only one matching ticket with winning numbers and if you own that. But what will happen? The prize is chosen at random from all those who have matching tickets. Then what will be the probability that you win if there are y number of other matching tickets? In that case, let's take W as the event that you win. So we want to find the probability of W where you have some other number of winning tickets. Let's say you have simple Y number of other tickets with the matching numbers. So altogether you have your ticket and other Y number of tickets. Altogether you have Y plus 1 number of tickets with the matching numbers. So from that you have to select only your ticket. So the probability of winning is 1 over Y plus 1. So overall, what is the probability that you win given that you have a matching ticket? So here we can use what we just derived right now. So the probability of event W, there is a condition on Y. So we can use this formula which we derived just now to find out the probability. So if you expand this, since it's a discrete variable, so you have probability of winning given that y is equal to simple y into probability y is equal to simple y, where y goes from 0 to infinity. And in this case, probability of y equal to simple y, that we can take from the Poisson distribution. Here we have derived probability y is equal to simple y, that is y 1 over e into factorial y. So that we can substitute here 1 over e into factorial y. And since this term is not only depending on y, you can take 1 over e out. So then you have summation y goes from 0 to infinity 1 over y plus 1 into factorial y, that is y plus 1 factorial. So here you can write 1 over y plus 1 factorial as summation y plus 1 factorial minus 1 over factorial 0, and then for this series we can replace that by e minus 1, right? This is, we can replace by e minus 1, and then that is, if you just further simplify, 1 over e into e is 1, 1 over e into minus 1 is minus 1 over e. So you will end up with the probability 0.632. That is, if you have some other tickets with winning numbers and if you own one ticket with all the matching numbers, you have a probability of 0.632. Or in other words, there is a 63% chance for you to win the ticket or win the prize even if you have the matching numbers. So that is something unfortunate. Anyway, this is the truth. So likewise, you can find out the probability using this conditional expectation as well. So I hope that it's clear with you, and I think we'll stop today's session from this point. Thank you.